Suppose we have a zero-sum game like this, and we want to find the a mixed strategy Nash equilibrium, and there seems to be many actions, so it's kind of hard to solve. So the good thing is we have multiple choices on the exam, so we can actually use these choices to make guesses. So let's start with the first guess, and let's say if the so the first number, the first action is the role player action, and the second action is the column player action. So the role player is suppose is maximizing, and the column player is minimizing. So we'll assume the column player is playing this, and let's check whether the role player's best response is to mix or not. So only way this is the best response is if the role player is indifferent between L, C, and R. So and let's check that. So we'll assume the column player is using this strategy, a third, a third, a third, and then the role player, in order for the role player to mix, in order for role player to mix, role player should be indifferent, should be indifferent between L and C and R. And let's actually compute that. So if the role player picks L, role player gets 0.6 with probably a third, 0.9 with another probably a third, and 0.9 with another 0. I mean, with another probably a third. So add them up divided by 3, so it's 2.4 divided by 3, so it's 0.8. Let's compute the same thing for C. 1 times a third plus 0.4 times a third, so plus 1 times a third, so which is 2.5 again divided by 3, so it's 0.8. We can do the same thing again, and now if I pick R, I will get 0.9 with probably a third, 0.9 again with probably a third, and 0.6 is probably a third. So if you compute it, it's symmetric to the first one, so it should be the same number. So indeed, role player is indifferent. So role player will mix, and anyway role player mix is the best response. So basically what this means is that is okay. So this is the best response to whatever that is. So best response of the role player given the column player is playing this strategy is any mix. So in particular, that contains this a third, a third, a third. So we need to check the other side and see if this thing is the best response to that as well. So let's check it here. So suppose the column player is playing a third, a third, a third. I mean, if suppose the row player is playing a third, 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 let's see the column player. If I play L, I'll get these three numbers. So note that don't read the matrix, read the payoff table the same way, because now I'm considering the column player. So L gets these three numbers, C gets these three, and R gets these three. And also, since it's a zero-sum game, you need to put a minus if you want to still want to find the maximum number. But here we can find the minimum number too, so let's do it that way. So 0.6 times a third, 1 times a third plus 0.9 times a third. Let's see what that is. So it's 2.5 divided by 3. So if I play C, I'll get 0.9 times a third, and 0.4 times a third, and 0.9 times another third. So what is this? So this is 2.2. Is it right? Yes. So now we know that C is better than L because the column player is the main player. So I'm actually trying to minimize. if you compute R, of course, it's symmetric to L, so it's 2.5 as well. So here, C is better than L and R. So C is preferred to L and R. So C, the only best response is playing C 100% of the time. So only best response is the action that always choose C. So what that means is the best response of the column player, if the row player is doing a third, a third, a third, is always C, it's just C. So in particular, it's not this thing. So it means they are not mutual best responses. One is the best response of another, but the other is not the best response of this. So, so the first one is not a Nash. So we checked that the best response to third, a third, a third is anything. So we probably know that this is another mix because again, it's any mix. So any mix contains this mix as well. So let's check whether the best response of the column player of 2/5, 1/5, and 2/5 is any mix. If it is, then we're done. Then B is the Nash equilibrium. So let's go back and check. Let's do it here. So suppose it's 2/5, 1/5, and 2/5. Again, let's highlight the column so that we don't multiply by the wrong numbers. So if I pick L, I'll get 2/5 of the time I'll get 0.6, 1/5 of the time I'll get 1, and 2/5 of the time I'll get 0.9. So let's see what that number is. So let's just do 5 over something. So 1.2 plus 1 plus 1.8. So this is 4 over 5. Hopefully this is right. And R, I'll get 2/5 of the time I'll get this. C, 2/5 of the time I'll get 0.9, and 1/5 of the time I'll get 0.4, and another 2/5 of the time I'll get 0.9. So let's do again 1.8 plus 0.4 plus 1.8. So it's 2 plus 2, so it's 4.5 again. Okay, so last one, R. R should be symmetric, but let's do it again. So 2.5, 2 over 5 times 0.9 plus 1 over 5 times 1 plus 2 over 5 times 0.6. So it's exactly the same number as the first one. So now it means the column player is indifferent between L, C, and R. So in particular, going back here, it means this is true. So the best response to this mix strategy is any mix. So in particular, this mix is also a best response. So now we have mutual best responses. Then this one is a mixed strategy Nash equilibrium.